All right, so I'll look through the programs that you've submitted. There's some things that we'll need to talk about. Um, a few things that we put together last time. There are ways to improve, so we'll talk about how to improve some things and how to do things in slightly different ways and so on. But the other part, or another part, not the other part, but another part of becoming good programmers and becoming good game designers and so on involves being able to solve a problem. So to solve a problem, I guess first of all we have to think about what is a problem? What does that mean, right? That word. If I ask you what is 1 plus 1, is that a problem? So I'm asking you, is 1 plus 1 a problem?
No.
Why not?
Because it is very easy to solve.
Yeah, we already know what to do, right? As soon as I said what is 1 plus 1, you thought 2. And it's easy for us, right? There's nothing to do, really. I mean, we know what to do. Now, what if we were in kindergarten? Then it might be a little more difficult, right? Maybe because maybe they don't know what that is yet, right? So it does depend on who you are, what a problem is, right? But if we already know how to do it, it's not a problem. What if I give you a page of 100 one-digit plus one-digit things and ask you to answer all those? Is that a problem? Well, I mean, I didn't give you any time constraint. No, so it's just, again, it's maybe tedious, right? It'll take us a little while just to write everything down. If there's 100 of them on a page, it might be, But it's not a problem. It's just a bunch of things that we already know how to do. What if we added a time constraint and say, okay, you have 1 minute to do these 100 one-digit plus one-digit things? Is that a problem?
You have a calculator?
It would take you longer with a calculator than it would without, right?
Depends on what the numbers are.
They're 1 digit each.
No,
right? It's 1 digit plus 1 digit, right? So that might be, it's not a problem, but we have to work at it's getting closer to being a problem, right? What if I gave you those 100 and say you have 10 seconds? It's getting how would we do that? How would we get that done in 10 seconds with 100 of these, right? Now we have to maybe think a little bit more about how we would get that done. What if I said, okay, you have to give me the answers first, and then I will give you the page with 100. Is that a problem? Then we would have to think about, okay, how could we, if we even, I didn't say that the answers had to be correct, but we were assuming that the answers had to be correct. So what could you do to kind of optimize or maximize your chances of getting correct answers? We'd have to think about it and think about, what numbers would be likely to happen. Are these randomly selected? So there's a lot of things so that could definitely become a problem. But going back to the 10-second situation, can you write down 100 numbers in 10 seconds? Say that again? Not with just one pencil. So what could you do? Yeah, maybe we could, I didn't say that necessarily. I didn't say that it had to be you writing all the answers. So we could split the problems up, right? Everyone gets their paper, and we say, okay, you do the first 10, and you do the next 10, and so on. and then you give the answers all back. So sometimes that's a possibility. If there's time constraints, then maybe we can split the problem up and solve it with multiple processors, right? Solve it in parallel instead of solving it all at once. So there's a lot of things we could do. Each individual piece of that is not a problem. But if we put enough of them together with enough constraints, then it might become a problem. So what are we thinking of with a problem is basically some situation where we are here, there's some solution over there, and there's something keeping us from getting there. We don't know where to go. We don't know how to do it. There's something in the way. Sometimes we don't even know if there is a solution out there. We just have a situation that we're trying to figure out, try to see, is there a solution? And if so, how do you get to it? Okay, so things like 1 plus 1, we won't consider that a problem. If we already all know how to do it, okay, that's not a problem. But you can very easily take something that you know how to do, and with enough extra things going on, it can become a problem. So if we have a problem, what's the first thing we need to do? What's the first step to solving a problem? Break it down?
Understand what the problem is.
Yeah, we have to understand, and that's part of that, right? We have to understand what the problem is. So step one, we need to understand that there is a problem, understand what it is. What does it mean to understand the problem? We have to think about things like, what do we know? What do we not know? What's important? What's not important? Everything that we can think about the problem, every aspect. So sometimes there are problems that we think we understand well, and we realize maybe not. Or we think that sometimes there are things that we think are more complicated than they actually are. Or sometimes we think that we don't have enough information. And we start thinking about it. What do we really know? What do we not know? All right, so the very first step, before we can do anything, we have to completely understand the problem. So a couple of you were in a course with me last term, and I think we probably talked about a situation of like how many gallons of water could this room hold? Did we talk about that? Right? So how many gallons of water do you think this room could hold? Well, is that a problem? Yeah, we don't know, and we don't know immediately how to answer that question. Right? So we would have to think about, what do we know and what do we not know, what's important and what's not important, and so on. So in that situation, what do we know? Well, we know we're talking about this room. We know what? Tell me some things. Well, what's important? What's not important? What do you think we would have to think about in order to answer the question of how many gallons of water could this room hold?
We need the square foot area of the room.
Okay, so what do we say? You say we need like the volume of the room. That is jumping to doing something. Before we jump to doing something, let's back up and think about what we actually know about the space. Right? What do we tend to do? We tend to, when we see a problem, we tend to want to do something right away. Before we do that, let's back up just a little bit and think about, what do we know about the room? What's important? What's not important? Okay, so let's see here. On this wall is this smart board. Is that important in terms of answering this question of how much water could this room hold? It's taking up space in the room, right? And actually, if you look at this and think about how many gallons of water space that is taking up, there's probably a lot of space that it's taking up. So it matters, right? So in answering that question, we would have to determine whether or not we're thinking of, is this board in the room or not? Are there other things that are in the room that might matter? Everything in the room takes up space, right? So in answering this question, we would have to determine, are we talking about with the stuff in the room or with the stuff not in the room? Because the answer would be different, even before we measure anything or do anything at all like that. We would have to, well, all of these kinds of things of what's here, what's not. That wall over there is a very blue wall. Does that matter? No, the color of that wall doesn't matter. What does matter about that wall? The clock that's on it. There's that recessed window over there. The camera up in the corner. Right? So those kinds of things matter. What else about that wall matters? Okay, so there are some outlets there.
The gratings on the very bottom of the wall.
Okay, there's things, trim around the wall and so on. What else about it? What is that wall made of?
Drywall.
Yeah, it looks like just drywall, right? So what would happen if we were to actually, I mean, in terms of how much water could this room hold, what would we have to consider?
Drywall would soak it up.
Yeah, what would happen if we actually did fill this room up with water? It would saturate that wall pretty quickly, and it would probably give way.
It would also probably ruin a lot of expensive equipment.
Well, so all of these are things that we would have to consider in terms of how much water could this room hold. Are we talking about in this kind of abstract sense of a room this size that's actually, or a space this size that's actually able to hold water, or are we talking about this actual room? Because those answers could be different, right? Physics comes into play at a certain point. You put a lot of water into a room and you get a lot of pressure, right? The walls would get saturated, eventually probably give way before we ever got the room, maybe, before we got the room filled all the way to the top. So there are real life kinds of questions. But let's just ignore real life and have this kind of theoretical room, right? It's just like this room, but it can actually hold the water if we decided to fill it up. All right, so all of this is part of understanding the problem, understanding exactly what we're trying to do. Because what happens if we don't really, really understand the problem, we are going to run into situations of solving the wrong problem, right? Doing a lot of work and coming up with a solution to something that's not really what we meant. If someone says, how much weight can you carry? And you create this theoretical version of you that doesn't have, you don't have bones, you have, I don't know, some kind of titanium structure or something, right? That's not the real answer, right? So we have to think about that. What happens as you start carrying things? There are other pressures. What happens in this room as you start filling it up with water? Things happen. So if we answer a question for this particular room, it could be very different than if we answer the question for this kind of abstract version of the room. Maybe this room could hold it, maybe it couldn't. There would be a lot of extra work to determine what kind of weights and so on. What might happen? Maybe the walls hold, but the floor gives way. And how much does water weigh? Does anyone have any idea how much water weighs? I think this was on there was a competition back in the fall with some professors and students, and it was, I think they used questions from like, are you smarter than a fifth grader? And it was one of the questions in there. So this, I guess, apparently is a fifth grade question. gallon is 8 pounds. So 1 gallon of water, I mean roughly, right? 1 gallon of water weighs 8 pounds. It's conceivable that enough water could cause a floor to break away, right? If it can't hold that much weight. Even if the walls didn't collapse, something else might happen. All right, so all of this is part of understanding a problem. All right, so we'll come back to this, but after we did understand the problem and have all of those pieces in place, what would come next in terms of solving our problem? Okay, well, finding all the variables might be part of understanding it, because the thing about what we know and what we don't know. So finding out what do we know, what do we not know, that might correspond to finding. But when you say finding the variables, do you mean like get values or know what the pieces are?
Oh, well, first know what they are and then getting them.
Okay, so knowing what they are is part of maybe the understanding part, right? Before we start doing something, what do we need to do next? Yeah, we would need to figure out how we're going to, instead of just starting gathering a bunch of data, let's think about what we're going to do, right? How are we going to go about solving that? And so we might call that devise a plan, right? Figure out a strategy. What are we going to do with this? So let's say we have a structure that's like this room. We don't have any equipment or anything in here. And we're not going to worry about whether the walls can hold it or whether the floor will give way, right? We don't want to, it'll be complicated enough. We don't want to overcomplicate. So we have whatever, the room you're in, you look around and you say, okay, we're going to have an idealized version of this room that can actually hold water. And so what kind of plans could we create? What could we do? Okay, so one plan would be to measure the room, get the volume of the room, and then do what? We have the volume of the room. It's so many cubic meters or so many cubic feet. I guess since we're talking about gallons, we should talk about feet, right? If we were going to talk about how many liters, then we should talk about cubic meters. What would you do if we did measure and had the number of cubic feet in this room?
Then you would need to say gallons.
Yeah, we would need to find some information that tells us how many, the volume of a gallon of water, right? So if we then had the volume of the room and we had the volume of 1 gallon of water, we could do a calculation to tell us how many gallons of water that the room would hold. All right, so that is a potential plan. Could do some. Now we have to think about that plan. How are we going to measure? All right, so if we get some tape measures, what will happen with the tape measure? All right, so if it's not long enough, right, we'd have to make sure that the tape measures are long enough. Otherwise, we're trying to measure to here and then measure from here to there. And what happens when you do measure from here and then measure again? Not as accurate. So if we had long enough tape measures, and then what? What else could go wrong, let's say, with that?
You might need a ladder so you can measure up to the ceiling.
Okay, we need to measure up to the ceiling. So, but what's going to happen? A tape measure is how accurate? If you look at a tape measure, you might be able to go down to a 16th of an inch. Some might even be measured to a 32nd of an inch, but probably about a 16th of an inch in most cases. So what happens if you're off a little bit? Would it matter? Yeah. If you're off a little bit over here and off a little bit over there and you're 20 feet across the room, right, it all might add up. Wouldn't be very much at any one time, but it could add up to several gallons of water to give us a wrong answer. So we have to be really, really careful. We also could have a problem with what? The person who's doing the measuring might just misread. So even though they were being very careful about placing it and so on, they might misread something. So we have human error possibilities. So we know about that in this plan. We have limitations of the technology, the tape measure, right? There are limitations to that. So could we improve that in any way to still use this same plan but do the measuring in a better way? By the way, notice that we have now switched to a new problem while analyzing this plan, right? Okay, what problems could come up with the plan? So when we're devising a plan, we want to think about these things. What can go right with it? What can go wrong with it? So getting the volume of the room and somehow finding out the volume of a gallon of water and doing the calculation could answer the question, but we have to make sure that we can measure the room well. So tape measure is a first approach to that. Are there any other ways to measure the room?
Also, check it against the laser measurement.
Yeah, so we could do a laser scan of the room. Right, a laser scanner can be pretty precise, much more precise than we could otherwise. We could do that. Any other ways to measure the volume of the room? We could find the blueprints, right? And maybe check the blueprints, check what's on there, and do some measurements in place to see if the blueprints are actually close to what's really going on, and then do the calculation instead of get the volume from the blueprints. Then, if it do some testing of it, say, okay, yeah, it seems like that they built the room according to the prints. If we can access those, any other way to measure? Okay, so we have several ways to try to think about implementing that particular plan, right? That particular plan says, let's get the volume of the room. We might have to calculate it in multiple ways or different ways to do it, to maybe even do it all of those ways and see, come up with an average or something of all of those. And then we want to, then we could do the calculations. We can find as long as we believe or trust in our source for the volume of a gallon of water, do that calculation. And notice that we have now, at least in our minds, have solved the problem, but we haven't done it yet, right? We just know what we're going to do before we started doing that. All right, so in finding the volume of the room, the easiest part is probably going to be measuring the floor surface area, right? The area of the floor, because it's okay. There's a doorway over here and a doorway over there, and that recessed window and so on. But we could measure that pretty easily. The height of the room is pretty easy to measure, we think, right? Except that ceiling has these drop tiles in place, and sometimes they've been doing work, and so one of these tiles is removed, and you notice that goes up pretty far above there. If you were to remove one of the tiles, you can see pretty far up there. Is that in the room or is that not in the room? Where does the top of the room stop? So if we look at the light, is that light in this room?
Yeah.
Does everyone think that light is in this room? Notice that light is above the tiles. So if that light is in the room, that means the top of the room is somewhere above the tile. Does that make sense? So where's the top of the room? How far up do we measure? If the light is in the room, and the light is above the tile, that means that we can't just measure from the floor up to the tile.
It would be until the next solid part of the ceiling, because that can expand across multiple rooms.
So in this, if you take one of these tiles out and look up there, it goes up another 8 or 10 feet above there. Is that all part of this room? So now that even just measuring the volume of the room becomes a more difficult problem, right? So what would we have to do? Before we can execute this plan of the volume, we would have to figure out what we mean. Where is our top line? Where are we going up to? And it is in this situation it doesn't happen, but it is possible that above this part of the ceiling that it's open into the next space. So would that be part of this same room if the wall didn't go all the way up above? So there's all kinds of things that then become much more difficult than we would think. So just how much water can this room hold? It turns out that this approach, there's a lot already going on. So what would we have to do? We would have to decide, all right, we can't really carry out this plan exactly yet. We have to make some other assumptions. We didn't realize that we didn't understand the problem as well as we thought we did. But now we do. So we go back to understanding the problem. Right? So that happens a lot. You're working through, and you have to go back to do something again. So maybe we say, okay, we're going to mark a line somewhere. We're going to say, maybe we decide it's the bottom of the tile. Maybe we decide it's the top of the tile. Maybe we decide there's some particular point, but we have to agree on that, where that point is or where that line is that we're going to consider the top of the room. The sides, the front, the back, the bottom, those are pretty clear to us. Right? There are walls and there's a floor. If we didn't have this type of ceiling with the drop tiles, then maybe the top would be answered for us. But in this particular type of room, that problem is not answered, so we have to figure out how we're going to deal with that. Again, that's understanding the problem. We just make a decision, right? We all have to agree. Are there any other possible plans? We don't want to just go with one of these plans, the first one they come up with, right? We want to think about other possibilities. Are there any other plans that we could have for calculating or determining how many gallons of water this room could hold?
You could, basically just run the pipe and start filling the water and see what happens from there.
Okay, so we could, since we made this kind of theoretical version of the room, we could have it sealed so that there's water's not going to leak out and so on, and just start filling the room up with water. If we started filling the room up with water, what would we have at the end? We would have a room full of water. But we don't know how much, because you just said just run the pipe and start filling it in.
Not necessarily.
So what would we have to do at that point? If we filled the room up with water, what would we have to do? Well, we don't know how, because we didn't measure anything. We'd have to pump it back out and do what as we pump it out? Measure it as we pump it back out. And then make sure we get every last drop of water cleaned up and measure it all in pumping it back out. But would that work? Yeah, if we could fill it up exactly to our line and let it all be, and get it exactly to that point and pump it all back out and measure it. Yeah, so we have this carpet on the floor, and we'd have to make sure we got every bit of water out of the carpet, right, to measure all of it, because I'm sure this carpet can hold a lot of water if it starts soaking it up. We have to get every bit of that water out. What could we do instead? Instead of measuring it on the way out, we could measure it on the way in, right? Fill the room up with water, but as we're pumping it in, we're measuring it, right? So we have a tanker truck shows up with, right, and it can measure how much water it's pumping, and we can fill the room up with water, measure it on the way in. Okay, so far we have three different approaches. One involves calculating the volume of the room, which we can do in multiple different ways. One involves filling the room up with water and then pumping it out and measuring it on the way out. One involves filling the room up with water but measuring it as we're filling it, so we know exactly how many gallons. Are there any other solutions that we could do, or other ways we could try to solve this problem?
Hire someone else to figure out the problem.
Okay, we could, right? We could say, hey, has this problem already been solved? So we could look something up, right? We could see, has somebody already answered this problem? Or will somebody else do it for us? That's a potential possible plan. Okay, so so it kind of comes back to a volume kind of question, right?
This goes back to the point that I thought like the carpet. So we can just like put the carpet until like we get every single piece off.
Okay, so that's kind of relating to, dealing with the carpet is relating to trying to make sure we have all that water measured. Are there any completely different ways that we can measure or try to answer this question of how many gallons of water the room could hold? Okay, so we could build a scale model of the room and then fill it up and measure and then scale that up to the room. How would you go about building a scale model of the room? What would you need? You would need the volume of the room, right? So it's back to the first approach, and then we're scaling it and building the scale model. And again, if we're going to build a scale model, we probably want to use the laser scanner to get the dimensions of the room, right? So there's some related things, some other ways that we could try to solve this. So what do you do with each one of those plans? You think about pros and cons. Can we do it? What's the best possible approach? Sometimes the best approach depends on what we mean by best. Right? Which of those that we've talked about do you think would give us the most correct answer?
I think it would be the pumping the water into the room.
Which of the two versions of pumping the water in?
The one where it measures on the way in.
Yeah, so we would get the most correct answer probably if we pumped water in and measured it on the way in. Right? We're very careful, filled very slowly when you get close to the top so water's not splashing out, and getting exactly to that line would probably give us the most accurate answer. Unless we did the laser scan with really high precision, then maybe that would. Okay, but probably filling the room up with water and measuring it on the way in would give us the most accurate answer. But can we actually do that?
Depends on how much money the school is willing to pour into the project.
It depends on how much money the school is willing to pour into the project. And was that pun intended?
Maybe. Also, a problem with the simulation would be you would have to assume that the program was written very precisely.
Yeah, so if we were going to use a simulation, the model, the scale model, we would have to make sure that whatever we're doing, is it a digital scale model, is it a physical scale model where we're printing out a 3D, a 3D image. So if we were filling this room with actual water, then we do have to think about the real life things of the walls giving way or whatever. So we go through all of those kinds of pros and cons of the different approaches, and then we do what? We decide on one of them. We decide, okay, this is the way we're going to do it. We may know that the way we're going to do it won't necessarily give us the best answer, or we may know some other potential issues with that. But we will have thought about that ahead of time. In devising a plan, we're thinking about all of those pieces. All right, so we decide we're going to do it one of these ways. Whichever way we decide, what do we then do? Carry it out, right? We say, okay, we have our plan. We know why we want to do it this way. Let's do it. Now, again, sometimes while implementing the plan, you realize, wait a minute, this plan has some problems. We have to go back and fix the plan. And whilst fixing the plan, we say, oh, wait a minute, I misunderstood something. You have to go back to here. Right? So these aren't necessarily a linear progression. Sometimes you have to bounce around. But if we have completely understood the problem and we have devised a plan that we have then settled on to use, and then the implementation phase. Now, what happens after you implement the plan?
Then you do the final calculations.
Well, so implementing the plan said things like, let's say we did the laser scan of the room, calculate the volume, and it says do the laser scan, calculate the volume, do the calculation of how many gallons of water that corresponds to, and here's your answer, right? So when you implement the plan, you have your answer at the end. What do you do with that? Yeah, we want to make sure, we want to look back, right? Do the analysis here. Let's look back. Did we implement our plan correctly? Right? Does that plan, was there a good plan? Did we really understand the problem? Does that answer the original problem? Right? We check every step of the way going back. And we also then, if we're satisfied with all those pieces, then we can look around to see if there is a way to apply this new knowledge to other situations. Right? What might we have learned during this? We might have learned how to use a laser scanner. Right? We didn't know how to do that before. Right? The 3D laser image of the room. Now we say, okay, now I can apply that new skill to some other things. If you got a laser scanner and learned how to use it, you would probably scan lots of things, at least for a while. Right? Create lots of digital images of rooms and so on. So once we've solved something, we want to see, can we apply this somewhere else? Can we use it in a different way? All right, but in this situation, let's say we had done all of this, we set everything up, we did all of our measurements, our calculations, came up with an answer, and we got an answer that says 8 gallons. What do we know? We know that's wrong, right? We still have to go through the look back, go through each piece, and try to figure out where we messed up. We might have messed up more than one place. So just because we find one error doesn't mean we say, okay, we fixed it. Right? We have to check everything carefully. All right, so we know that it is not 8 gallons. What if the answer came back at 14,738 gallons? $14,738.2 gallons, right? If it were exactly 738, we would say, no, that's probably not right. But it came out 738.2. I have no idea if that's the right answer now. We don't know immediately that it's wrong, but we don't know that it's... What do we still have to do? We still have to check every single piece, right? So even if you think the answer is right, you still check. If you know that it's wrong, you check. If you don't know whether it's right or wrong, you still have to check. Which of those is the easiest situation to check? Well, if it's 8 gallons, we know there's a mistake. The downside is, as soon as we find one, we say, oh, I found it. I found the mistake. No, you found a mistake. Maybe there's a whole bunch more. What if we had an answer that we're pretty sure is right? We still don't know if there's a mistake, right? And if we have no idea, so all of them are difficult in terms of the looking back portion, right? All of them involve a lot of work of trying to figure out, is this accurate? Is this correct? All right? Now, as people, what do we tend to do when we're faced with a problem? Where in this process do we tend to go? Well, I mean, if you're faced with a new problem, where in this process do we tend to jump to? Do we? We immediately start trying to do something, right? Most people, when faced with a problem, immediately start trying to do something. Now, if it's a situation that you're really comfortable with, then you already understand the problem and you recognize all of the pieces just by looking around or whatever. But most of the time, we tend, as people, to jump to implementing the plan when you don't even have the plan and don't know for sure whether you understand the problem. So what do we need to do? We need to get in the habit of slowing down a little bit when faced with new problems. Do I really have all the pieces? Do I know what all the pieces are? Do I know what's important and what's not important? Do I know how things fit together? Do I know what's happening? Now, what could I do? We don't want to necessarily jump to a plan that's always worked in the past, because the problem might be slightly different this time. we don't want to implement until we've thought about the different pieces. So these 4 steps are common sense, right? It seems like, oh yeah, obviously that's what you should do. Understand it, figure out what you're going to do it, and then check your work. We tend to not do that. These 4 steps, named after a 20th century mathematician named Polya. There's an accent somewhere. I think there's an accent on the O. I think it's like that. But he realized that a lot of people aren't very good at solving problems because they haven't practiced solving problems. And so he wrote some books and did some things. And basically, these things seem obvious, but then there's a lot to do in each place. And how do you, what do you look for in trying to understand a problem? What do you think about when you're trying to come up with a plan? So if you practice and work at things, you get better and better and better at solving problems. So let's look at an easy real-life situation. You're driving to campus and it's exam day, and you get caught at a traffic light. It won't change. Is that a problem? You're here and you need to be there and there's something in the way, right? That's exactly our definition of problem, right? So the light won't change. What do you do? Well, let's understand the problem first, right? What is involved in understanding the problem?
Possibly what's causing the light to stay red.
Okay, so what's causing the light to stay red? Might be, do you really care what's causing it? You don't really necessarily care what's causing it unless the thing that's causing it is that you haven't pulled up far enough, right? If it's red because you haven't triggered the light to change, okay, that might be an important why. But if the light's just broken for some external reason, we may not really care about that. What do we care about? How to get around, how to get through the light, whatever, how to get to where we want to go. But sometimes it might matter what might be causing it. What else in understanding the problem? How much time do we have? And we can't tell that right now, but if you were in that situation, you would be able to know how much time you had. What else could we do in terms of understanding? What else do we need to think about in terms of understanding the problem?
Knowing how much traffic is in front of us.
Okay, how much traffic is in front of us? If we are the first car in the queue, it's different than if we're the 7th car. Right? Our possibilities are different.
Kind of with that, are there any people around to see if you just go through the light?
Okay, so are there people around? So we're thinking ahead to some possible plans while still understanding. We're thinking ahead. Are there people around? Is running through this light an option? Is it a possibility?
What are other people doing
If there are other people around, what are they doing? This is all, we understand all of these things just by looking around, right? And so we don't have to go through like some very careful, okay, now let me write down all the people. No, we look around, we recognize these kinds of things. Are there other people around? What are they doing? How much time do we have? Where am I? Are these one-way streets? Can I, is there an option to be able to maybe turn? Am I close to an alleyway that I could turn down? What are these? All these things are part of understanding the problem, taking in all of the information. What's not important in this? The type of car you're driving. Doesn't really, well, I don't know, it might. Right? It's like if you're in a really big car and there's like a tiny little alleyway, then that might say, okay, you shouldn't really go down there. But if you're in a smaller car, then maybe that's okay. So the type of car you're driving might matter in terms of some potential plans, but the song that's playing doesn't really matter, right? The sign in that window over there may or may not matter. Depends on what the sign says or what kind of window it is. So there's a lot of things that we recognize aren't important in the situation, but then the things that are. All right, so what possible plans would we have? You've already mentioned, hey, can I run through this? Can I run the light? All right, so that's a possible plan. Is a U-turn possible? Mention the alley. Can you Can you turn down an alley? Could you drive across a parking lot somewhere?
Are you allowed to make the right-hand turn?
Are you allowed to make a right-hand turn, or in certain situations, a left-hand turn on red? If you're first in the queue, if you have a one-way street, two one-way streets, you would be able to turn left on red, or possibly the other way, turn right on red.
Wait, is that a real thing?
Yeah.
Can you park your car?
I'm sorry?
If you can't drive anywhere, can you park your car?
If you can't drive anywhere, can you just park your car and walk to get to the exam on time? Even more extreme, just leave your car where it is and get out and run, right? That's a possibility. What other possibilities do we have? Okay, so we had mentioned the actuator, right? Pulling up or back a little bit, see if you could trigger the light.
Why not just call or email the professor and say you're going to be a couple minutes late?
Okay, call or email the professor and say, hey, I've got this traffic issue, I'm going to be a little bit late. What else could we do? Get out and push the button on the crosswalk to try to trigger it in a different way?
Pull up a little bit.
Okay, that was, the pulling up a little bit was mentioned.
My bad.
Oh, it's okay. What else? What are we doing during all of this time at this light? What are we doing? We're waiting. Isn't that a plan? We just wait for the light to change. It might not really be as long as you think. So while we're doing this thought process, and this is happening, if you're driving, it's happening really quickly, but when that is going on, you are at the same time implementing a different plan, which is wait on it. So there's a whole bunch of possibilities. And the longer you drive, the more of those possibilities are readily apparent to you. But we eventually have to decide what we're going to do. I mean, you had mentioned earlier about why is the light broken? Okay, so we ring the public safety and say, hey, this light is not working. Instead of me, right? So the professor, they say, all right, this light's not working. Can you fix this light? And they push some button somewhere in an office and it fixes the light. I mean, that's a possibility. But what happens? There's a lot of different things we could do. Maybe you try one thing and it doesn't work, so you try something else, right? You wait and that's not working, so you pull up and back. That doesn't work, so you get out and push the crosswalk button. That doesn't work. Right? So you might implement several plans of the options. But I can tell from when he said it that more than one of you are like, yeah, I'm running this light. All right, so we think through all those plans. We decide we're going to run the light. And that's the plan, right? The plan is to run the light. So we run the light directly into the side of a police cruiser. Our plan was run the light. Let's look back. Did we implement our plan correctly? Yeah, our plan said run the light. We did.
Well,
what was the problem?
you didn't check the traffic.
We had a bad plan. Our plan says check for traffic first. Right? It didn't say that, but it should have said that. All right, so let's go back in time a little bit, and okay, that was the plan. The plan was to check for traffic first. So we check for traffic. And now, when checking for traffic, you mean don't go if there is traffic, right?
Yeah.
So there's traffic. Okay, wait. There's no traffic. So now we run the light. Hit the pedestrian in the crosswalk. Was that in our plan? Did we say look for people? No, you said look for traffic. Okay, so wait a minute. Our plan should have been a little bit better. Look for vehicles and for people. Oh, see, so you caught me before I got there because I was going and that poor puppy was right in the middle of that crosswalk, right? So look for anything that could be in the way.
I think we're also forgetting the more illegal hit and run off. It's a plan.
Okay, it is a plan. It is a very bad plan, but it's hit and run. Okay. Wow. So what happens? Let's say the way we meant, there's nobody, there's no cars, there's nothing. We run the light. don't get hit. Nothing happens. But as soon as we get through the intersection, the police officer was parked on the corner right across from us and pulls out, and we're caught. Now, we were looking for traffic that was moving. That traffic was sitting still. It wasn't traffic, right? It was a car sitting still. So what does that mean? Did we implement the plan correctly? Was it a good plan? No, because it didn't look for everything. All right, so we take care of that now. Okay, no cops. All right, we run the light. We come to class. We take the exam. We get an A. And then what? 2 weeks later, we get a ticket in the mail. Because what did we not look for? We didn't look for the traffic camera.
Going back to the one where the cop pulls out, for that I want to say that also actually depends on the town, where you're at, because I have ran red lights before and there's a cop just right there and they don't care by the time you're doing it.
Well, this one did because we said you got pulled over, right? So
If you were waiting on the light and the light took too long and it was like not changing and was broken and you ran it, cop probably would not really care. They were like, oh, the light must be broken.
I mean, there are situations where you could explain it away, but there would still be some explaining to do, right? Which is going to make you later for the exam. So what happens? All of these different plans, when you implement, you look back and you say, okay, did I implement the plan correctly? You might have implemented the plan correctly, but it could have still been a bad plan. Okay, so let's look at it from this situation. This time, we did all of the checks. We ran the light. We got through. There's no traffic camera. Nothing ever happens, right? We took the exam. We got a good grade. We went home. Never got a ticket. Everything was fine. Is that a good plan?
No.
It worked that time, right? It's not something that we would want to file away as, oh yes, this will always work. In other situations, sometimes, if it works that time, then it will always work, right? For different things. So what happens? Even something as simple as a traffic light, we go through this. Now, what do we do in real life? We do very quickly mostly understand the problem just by looking around. We run through some potential plans really quickly. We probably should take more time running through those potential plans because thinking about pros and cons, not just what can I do, but what is the downside to doing that. Implementing the plan, making sure we implement it exactly, and then this look back and around portion. All right. So what happens in the looking around at that case? The idea would be, I guess, first of all, if you've gone through the red traffic light, looking around for that cop, right, to make sure we're okay, but really looking around for other situations. This worked. I'm pretty sure this is now a good way to tackle this kind of problem. What do I do? Where can I apply this in future situations? Or this was a bad thing, right? Even if you solved it and you got a bad thing, okay, now where can I apply this bad result? Don't do it this way, right? Don't do this in similar kinds of situations. All right, so what we have on Blackboard is an assignment with 10 questions. They're just kind of logic, kind of problem-solving kinds of questions. Some of them seem very easy, but they might not be. Some of them seem much more difficult, but they might not be as difficult as they seem. Some seem difficult and are. Some seem easy and probably are. But we don't know going into a problem what is really going on. So we want to not just jump to doing something. We want to get used to thinking through, what do we really know? What all is going on in this problem? What do we have? What do we know? What do we not know? What's important? What's not important? So one of these questions we will look at together for a second. I think some of you may have seen this before, so don't say anything if you have. Here's a collection of symbols. What comes next? these symbols have some meaning. And we want to figure out what comes next in this sequence of symbols. So this line moved from the bottom to the middle, and now going to move to the top? Maybe.
There would be another symbol before.
Or maybe the thing after the is a symbol.
Well, there's two symbols in between.
So there's this, and there's this, and there's two symbols in between, so you think there needs to be another symbol, and then there'd be this with the line on top?
Yeah.
Okay. One student once said that this next symbol should be this one again. And here was her explanation. This is a weightlifter, a power lifter. So they have the bar on the floor. Now they're flexing. Now the bar is chest high. Now it's over their head. And what happens after the bar is over their head? Drop it again, right? Put it back down on the ground. What do you think?
So what would the 8?
Yeah, what's this? Right? Just skipped over that one because it didn't fit in with the narrative. Can't skip that one, right? It's part of it. All right, so that would work if that symbol weren't there. We could say, okay, yeah, I can buy that. I can believe that. But that symbol is there, and so we kind of have to say, no, probably not, right? What do you think? So you said that you think that not this one, but the next one is going to look like that with the line on top. So what comes next, though? The 8 again? All right, let's see here. Let's go back to the steps. The first step in solving problems is what? To understand the problem. So what does understand the problem involve? What did we say you have to do when you want to understand a problem? Get all the information. So we have all the information. This is all the information we're given. Then what do we have to do with that information? We have to think about what's important and what's not important. So what if we get rid of what's not important? Sometimes when we get rid of what's not important, we can see what really matters. Does it make sense? Can we tell what comes next? Can you tell what comes after that? Yeah, we can see what's happening now, right? So what happens, often we have a situation where there's a bunch of unnecessary things. And if we can get past that, now, you can't tell that that's unnecessary until it's gone. And then it's like, oh, okay. So what happens is an awful lot of the time, we are faced with situations where we have too much information. It's the wrong information. But if we can get through it to the important part, we can solve the problem. Sometimes it's the opposite problem, that we think that there's not enough information, so we have to work really hard to figure out what do we know? What can we figure out from where we are? What is hidden in here that I'm just not seeing? We don't want to, on these 10 questions, we don't want to guess unless you absolutely have a good reason for making a particular guess. All right, so making a guess is a valid problem-solving method, but only if it's a descriptive guess, right? If it's when you make this guess, if the answer is no, then you know what that means. Or if it's yes, then you know what that means. You can rule things out. So we don't want to just guess at things. We want to have very precise reasons. If you get to a guessing scenario, you want to be able to say, this guess tells me this information.
I just realized what you erased are the numbers backwards.
Yeah, so what did we have? When you look at this situation of what got erased, there was symmetry. Right? Everything was folded over that line. So it turns out that this idea of symmetry we're going to use that a lot. We'll use it in this class a lot, and you'll use it in other ways later. That solving half of the problem, or looking at half of the problem, or half of the data, is sometimes better than trying to look at all of it. If we kept looking at all of that, I don't think that we ever get anywhere. Even if I drew the next symbol for you, I don't think we get any. If I drew the symbol after that, the symbol after skipping this one and going to the next one doesn't look like that. What does the symbol skipping the next one and going to here look like? Yeah, maybe a triangle. In my case, it would be a triangle like that. Right? So what happens when we sometimes look at just the important parts? Other times, we have to fill in the gaps with other information that we already know or things that we know from outside. All right, so what I want you to try to do is work on these 10 problems, but don't just jump to doing something, right? Do these slowly. Go through very carefully. Think about what we know and what we don't know. Don't just jump to answers. It's not getting the answer that's important. It's the process that matters. All right?